All right. Well, I've graded the homework assignment that you turned in last time. And, you know, that handout problem's a tricky one. And some of you did a really nice job, like made my solution look really embarrassing by comparison, how detailed and neat some people did their work on the handout problem. And some people, I think, were too intimidated to even attempt it. So if that's you, if you sort of took a look at it and decided it's not worth it, at the very least, please look at the solution so you can familiarize yourself with what you should have done. And that solution is posted online. Sounds like some people have gotten started on problem 43 of the homework assignment. These other two are related to water hammer and surge tanks, which is what we're doing today. So that assignment's due next Tuesday. Any questions before we get started? All right, well, you guys about wore me out last time. I was here till 5:30 working on troubleshooting spreadsheets, but if you still haven't got your example Hardy Cross spreadsheet working okay, then please stop by, because I want you to have one that you know is functional and working right so that you can use that as kind of like a reference as you work on the homework problem. All right. Somebody on some forum one time asked, what's the most expensive mistake you ever made? And here was one of the popular replies. I'll give you a moment to read that. All right, $800,000 down the drain, right? $800,000 of damage. Now I have an argument with their technical description of what a water hammer is. It's not a burst of air, but it is something that can definitely find weak spots in a pipe. And so we're going to be talking about what causes water hammer today, some of the techniques we have for managing it. It's kind of just like an interesting physics problem. And I don't remember why I put this picture of a Ferrari underwater. I guess to illustrate the cost of flooding. So let's look at water hammer. All right, this is a water hammer that somebody is observing at their house in the sink. So it's kind of an interesting phenomenon because it affects both individual homeowners and then also really complicated pipe networks as well. All right, so someone is adjusting the flow rate. So there aren't machine gun bullets inside the pipe somewhere. That banging back and forth is related to the time it takes for a pressure wave to travel from the valve that's being closed back to a tank. So that's one instance to illustrate water hammer. Here's another. Somebody had the problem with their washing machine.
Okay, you heard that noise come from the pipe. We're going to get closer, we're going to see the action over here. You see the whole pipe shape, that's from the cold water valve. And there's one solution to take care of this problem. You actually have two. You either lower down your house water pressure, or you have to get yourself one of this guy called the a mini water arrestor.
All right, so this is basically like a shock absorber. And having this in line, would give some place for that shock wave to be absorbed so that it's not causing like the surging in the cold water line that you saw. And the reason why that surging is happening in the pipe is that the valve inside the washing machine, it looks like an expensive washing machine, right? But it's metering water into the basin in surges. And it's probably an electronic switch that's opening and closing a valve very quickly to just have a few more drops of water come in. It's probably, machines like this are load sensing, where it adjusts how much water is added to the washing machine based on the amount of clothes that it senses. It spins around for a moment and tries to calculate how much is there. And so it's really sophisticated, except for the fact that the valve is being instantaneously opened and closed. And that's what's causing the water hammer, is the fact that the valve is being closed too quickly. And this is a nice video that kind of explains a little bit more about water hammer. So this will be the last one we watch here.
Column of water moves from its source at the main to the valve outlet. This could be 100 pounds of water flowing at 10 feet per second, or about 7 miles per hour. Closing the valve suddenly is like trying to instantly stop a 100-pound hammer. A shock wave of about 600 psi slams into the valve and rebounds in all directions, expanding the piping and reflecting back and forth.
So look at what caused that shock wave. Watch the hand.
Or about 7 miles per hour.
Watch how quickly he closes the valve.
Closing the valve suddenly is like trying to instantly stop a 100-pound hammer. A shock wave of about 600 psi slams into the valve and rebounds in all directions, expanding the piping and reflecting back and forth along the length of the system until its momentum is dissipated. By closing the valve slowly, the velocity of the water is reduced before the column is stopped. Since the momentum of the water is decreased gradually, damaging water hammer will not be produced.
All right. So it's a problem that's largely avoidable by the speed that a valve is closed. Let's talk about what causes the problem in the first place. Just as an illustration, we're going to go through a series of images and talk about what happens as the water is flowing freely and then as the valve begins to close. So what we're looking at right now is water has an initial velocity of V0, and we have an elevation datum here that all of the Z measurements are taken from. You can see that there are head losses, so the H sub F is just related to pipe friction as water is traveling through the pipe. We have a loss of energy due to the interaction with the pipe wall. And then here is the hydraulic grade line, the lowest dashed line there, which takes into account the pressure, and the pressure is decreasing because of the change of energy. So just initially we have steady state conditions. Water is flowing without any changes over time. And we could take a look at one section of the pipe and put a control surface around that, and we're interested at the flow in and the flow out through those control surfaces. And you'll remember back to fluid mechanics when we were talking about the momentum equation, we said that we could find out what the imbalance in forces are by looking at the difference between the velocity in and the velocity out. And so there was the jet impact experiment, for example, where it wasn't necessarily the magnitude of the velocity, but it was the direction of the velocity that was changing by those little plastic deflector plates. And because the deflector plate was changing some component of the velocity, in our case the direction of it, that caused a force. And so the same thing is going to be happening here as the valve is closed. In steady state, V in equals V out. But close to the valve, for just the briefest of moments, the velocity out of this control volume is going to be less than the velocity in. Because water is pretty much incompressible, but it's slightly compressible. And so that means that there's going to be a very slight reaction time where the velocity that's coming into the control volume is faster than the velocity that's going out. And so the water is in effect piling up. There's a momentum there because of the sudden stop. So here, now the valve has been closed, and there's a lot going on in this diagram, so let's talk about some of the different pieces of it. First of all, you can see the letter C here. And what that C is representing is the speed of the shock wave that's traveling away from the valve. And so closing that valve meant that the water was piling up and there was like a transfer of momentum to the valve, and now that energy is reflecting back towards the origin, towards this tank. At the same time that that's happening, there's an increase in pressure inside of the pipe. There's a lot more energy now close to the valve, and so you'll notice this delta H here is indicating that there's an increase in energy in at least part of the pipe. Now the shock wave is still traveling towards the tank, and so the increase of energy isn't everywhere. It's just in the section of the pipe that's been affected by the shock wave. Now, pipes are made out of plastic, metal, sometimes concrete, but all of those materials can expand when there's an increase in pressure. And that's what's happening here, is that as the pressure wave is moving towards the reservoir, at the same time, the pipe itself has expanded a little bit because there's so much extra pressure here. And so the pipe is flexing outward, and that means that it's drawing additional water into the pipe. Now, the bulk flow, water isn't flowing through the valve, but a little bit of extra water goes from the reservoir into the pipe simply because the pipe material is swelling. And so it now has a greater interior diameter than it originally did during steady state. Any questions so far about what I've described? Yeah.
What about faucets that are like motion sensing stuff once you move your hand to shut off?
Yeah, those are causing shock wave, and it's pretty common for, like at an airport is where you often see those motion sensing water faucets. Like in big facilities like that are more sophisticated than an old house like I live in, or they'll put in some of those those shock absorbing pipe fittings to kind of reduce the effects of water hammer. So it's probably why we don't notice it more often, is just that there are a lot of things out there. Valves get closed quickly all the time, and so they kind of have to build in relief valves and surge tanks that help to mitigate the problem. Are there other questions? Okay, so the valve is closed, but water's still going into the pipe because the pipe is swelling. And the pressure wave, the shock wave is going back towards the tank. And the material properties that are important here is the fact that water is slightly compressible, although not very compressible. And then the pipe is also flexible. It has an elasticity so that the pipe walls can expand as that pressure wave is going through. Okay, so now in this picture, the pressure wave the shock wave made it all the way back to the tank. And what this is showing with the little dotted line is that the pipe has expanded. And so it's holding a lot more water than it normally would under ordinary conditions. And that's why, right now, this is showing that there's more energy inside the pipe than there is inside of the tank. Now normally, if the valve was closed and it hadn't started this water hammer effect, there would be the same amount of energy in the tank as there would in the pipe. That the line of energy would simply just be horizontal, extending from the water surface. But here, there's more energy in the pipe than there is in the tank because of the stored energy in the pipe that expanded. You'll also notice that the velocity is zero because it's sort of like a pendulum swinging back and forth, and at this instant in time is when as much water that's going to go into the pipe is there, and now, as you might guess, it's going to start rushing back towards the tank because water flows in the direction of from high energy towards low energy. And right now there's more energy in the pipe. And so what's going to happen is that the water that's in the pipe is actually going to be going the wrong direction just briefly because there's too much water in the pipe because it's swelled. And so now you can see this velocity arrow is going back towards the reservoir at the same time that a secondary shock wave is making its way back towards the valve again. And so the C was talking about the speed of the pressure wave, and the energy is decreasing in the direction of the energy wave. But the problem, of course, is that that wave is, again, if it encounters that closed valve, that wave will get against the closed valve and it's just going to reflect back towards the reservoir again. And so it can bounce back and forth dozens of times before it finally wears itself out. You know, there is a little bit of energy loss. Each time the pipe expands and contracts, it's kind of dissipating that pressure wave ever so slightly. But it can literally be dozens of times before finally the wave kind of wears itself out, depending on the length of the pipe and what the pipe's made out of. So water compressibility is at the heart of what causes the problem of water hammer. Were there any questions about this slide? Okay. These images are of different configurations of water at different pressures. And of course the water molecule itself isn't changing its orientation in terms of the angles that the hydrogen is bound to the oxygen, but there are different configurations of packing as the pressure increases, and that's why there is a slight compressibility of water, is because you can make a little bit of extra space depending on where the water molecules are in reference to each other. Compressibility is relatively unaffected by temperature. You can see that this is a fairly flat curve for the compressibility of water. But when we say compressibility, we're talking about some unit change of volume relative to a change in pressure. And last semester we talked about the bulk modulus of elasticity, and compressibility is the inverse of that. The calculations that we're going to do are with the bulk modulus, but we can think of the inverse of the bulk modulus of being the compressibility, and that is how much of a change in pressure causes a change in volume, a unit change in volume. All right, so here's the bulk modulus, along with the table that's in the book related to the bulk modulus of water at different temperatures and for different pressures. So the bulk modulus E sub V is the specific volume being the volume occupied by a unit of mass. And so 1 kilogram of water, for example, occupies 1 liter of space. And so what we're asking with the bulk modulus of elasticity is how much of a change in volume is there for a certain applied pressure. And so the units of bulk modulus are simply units of pressure, newtons per meter squared, or if we're working with traditional units, it may be pounds per square inch, but it's units of pressure because the units of both the specific volume and the change in specific volume cancel each other out. So that would be units of cubic meters or units of liters. What's that? Oh, right, yeah. Great question. So like, what if you're right on the edge? I guess what I'd do is I'd average the two. Yeah. Are there other questions? All right. So celerity, I put this up there just to make things extra confusing. It's celery. Yeah. Well, calling into question my vegetables here. It's not asparagus. Okay. It was pretty small though. In the notes maybe black and white. All right, so celerity is the velocity of a pressure wave, and in theory the velocity of a pressure wave, like if we were going to measure it in the open ocean where that pressure wave could travel unconfined and unreflected by a boundary wall, then it would travel at a speed related to the bulk modulus of the fluid and the density of the fluid. And so, generally, a typical theoretical wave celerity is 4720 feet per second or more than a kilometer per second. And so that's how quickly pressure waves move through water. However, in a confined space, like in a pipe, the velocity of the pressure wave is different. And it's affected by the material properties of the pipe itself. And so E sub V is the bulk modulus of the water, but E sub P is the bulk modulus of the pipe. We also have to know the thickness of the pipe relative to the diameter of the pipe. And so what this takes into account is essentially that action of the pipe flexing, or it being somewhat elastic as the pressure wave is moving through the pipe. And so in the example that we'll work today, what we'll find is that that slows down the shock wave as it's traveling through the pipe compared to the speed that the pressure wave can experience in an open situation. The confinement of the pipe slows it down. So C will be lower than C prime. Now, the whole key to avoiding the issue is closing the pipe slowly. And what we want to do is make sure that we're closing it slow enough that any kind of shock wave has an opportunity to travel to the reservoir and back. We want to close the valve slower than that travel time. And so here in this formula, the L that it's discussing, the L, the length of the travel time, it's actually, I should change this, it's 2L is the travel time that we need to be concerned with. So if you have that printed out in your notes, let's change that to 2L, because L is the pipe length, but the time that the critical time that we have to be careful about is the round trip distance, because the pressure wave is going to make its way starting from the valve, go to the tank, and back to the valve again. And if the valve is only partly closed by the time it makes that round trip, then the accumulation of pressure doesn't occur. And the video we were watching, the last one where they had some sort of a printer that was showing the increase in pressure, I'd be interested to know their setup, how long the pipe was, because they had a reservoir somewhere at the end of it. But when he closed it slowly, basically what happened there is that the pressure didn't increase in the pipe because the water was still able to, the momentum was slowed gradually as the valve was partially open. And we can calculate the magnitude of how much pressure is increasing, the maximum increase. Like if you close the valve faster than this time, T sub L, then this is the pressure that you'll get. And it's related to the initial velocity, the celerity, and then the density of the fluid. So the initial flow velocity really is the only thing that we have control over. We can't change the density of the fluid. We can't change the speed at which the pressure wave is traveling. I mean, not in any real sense. We're not going to adjust a pipe diameter to try and control that. But we can ensure that the velocity is either low in the pipe, and that will help protect you against a high surge in pressure, or we can have some sort of like an automated system for closing the valve at a speed that's less than that travel time. So for you to get your hands dirty with these equations, I wanted to give you this example. We have a pipe that's 2,000 feet long. We know it's made out of steel. 4-inch diameter. So the 4-inch inner diameter pipe has a wall thickness of 0.2 inches. It's carrying a flow rate of 0.6 cubic feet per second. And here are the material properties of the pipe, and here are the fluid properties of the water. And so we want to calculate, first of all, what pressure increase could you see if the valve was closed instantaneously? And for our purposes, what instantaneously means is faster than that round-trip travel time. And then in part B, you should calculate how much is that round-trip travel time that we need to be concerned with so that we can avoid having that maximum increase in pressure. Do you have a question? Mm-hmm.
What happens if that hammer effect takes place in the pipe, changing how it comes with gas?
Well, inside the pipe there's no oxygen, and so like there's only going to be an explosion if it's exposed to an oxygen source and a heat source. And so, I think you could have water hammer and it wouldn't necessarily explode. But yeah, we call it water hammer. I wonder if there's gasoline hammer. If you're at the gas station and you're just squeezing that dispensing handle really quickly, I bet that they probably have thought of that and have those little shock absorbers like we saw in the washing machine video. All right, so I'm going to pause this record. All right, so I found the velocity first just to have it available when we needed it, 6.875 feet per second. Then we're going to calculate the theoretical wave celerity, which is the speed of a shock wave in the open water, and that should be 4874 feet per second for the conditions that are described. And of course, these fluid properties are based on a certain temperature of the water, and so it could be variable depending on what temperature the water's at, but not by a lot. Now, things change more based on the conditions in the pipe. And so in our case, we were working with a 4-inch pipe that has a 0.2-inch thickness. And I've done this example in the past where I converted PSI into pounds per square foot, and I converted the inches to feet, and these inches to feet, and this PSI to pounds per square foot. But then it occurred to me that that's not really necessary since the units are going to cancel themselves out. We have a length unit in the numerator due to the diameter. We've got a length unit here due to the pipe thickness, and so it can be either in feet or you can leave it in inches and it's going to cancel out. And then the same is true for the two-bulk modulus, that those units are going to cancel out. So it can be PSI or PSF, either one. And what we end up with is the new celerity, and so the pressure change, we could see up to 58,000 pounds per square foot, which is about 407 psi. Anybody else get the same number for that? Okay. So that would definitely be enough to explode a water heater. Now, these are pretty unusual circumstances, though. We're talking about a 4,000 foot travel distance, and so the physical length of the pipe in this one is 2,000 feet. So that's about a third of a mile. And it would be unusual that you'd have an uninterrupted segment of pipe quite that long. But if you did have a section of pipe that long, it would be especially important to close the valve slowly. And so the risk factor for having a big change in pressure is partly related to the velocity of the pipe, but then the travel time here, if we calculate the minimum close time, in this case it's about a second, and so you have to be more cautious about the speed that you close the valve for a longer run of pipe, because that longer run of pipe is going to give more time for the shock wave to get all the way back to the reservoir before it starts heading towards the valve again. And so short segments of pipe can be closed really quickly without the risk of water hemorrhage. It's the long sections of pipe, and maybe that's why with the, in addition to the shock absorbing fittings, we don't usually have sections of pipe quite this long, and so that's why it becomes less of an issue how quickly the valve is closed. Surge tanks are one of the ways to relieve that shock wave and to give some place for the water to go so that the pipe doesn't have to expand. So it's kind of preventing the water hammer from ever occurring. And a surge tank is just a reservoir. In this case, it's depicted just as like a branch pipe. And you essentially remember that more water went into the pipe when it was all the way expanded. Back in the case of here, those dashed lines were representing the fact that some additional water had gone into the pipe as the pipe expanded. And so rather than allowing the pipe to get so much embodied energy and then later on contract, what the surge tank does is just give it an alternate location for the water to go into. And how high the water surge is going to be depends on the length of the pipe, the area of the pipe, the cross-sectional area, and then the diameter of the surge tank is going to affect the cross-sectional area of the surge tank. And so if you have a very large diameter surge tank, then the water level isn't going to go up or down very much during a surge. But if it's a relatively narrow surge tank, then it's going to have a lot more height to it for the water to fill up that volume. So let's take the same case that we just were solving, where the physical length of the pipe is 2,000 feet, 4-inch inner diameter, and the flow velocity that we know. How big around, what would the diameter need to be for a surge tank if we only wanted the water depth to increase by a maximum of 1 foot during the surge? So in other words, solve for the diameter of the tank, which is going to go into the cross-section of the tank, assuming an S max of 1 foot. So I was glad to hear your skepticism. People are saying 18 feet, that seems like a lot. That's pretty big. So that means you're thinking in terms of reasonableness. It is that big, but that you're evaluating things against what seems normal. You know, that's just a 4-inch diameter pipe, right? But think about the volume of water in a 4-inch diameter pipe over 2,000 feet. It's a lot of extra water that's going to be in there. So if we didn't want to make a tank that big, then of course we just have to make it taller. But either way, there's a certain volume of water that has to be contained during that surge, and if we provide a place for the water to go, then it relieves the pipe of the necessity of expanding during the surge. Yes?
Like in a household plumbing application, how do you determine the length of the pipe from like where the tap is to what's considered the reservoir?
Exactly, yeah.
What is the reservoir in a household plumbing application?
Yeah, I've wondered the same thing because where I live, we have a lot of boil water advisories because it seems like, I don't know why, but we have a lot of boil water advisories, probably 6 a year. And they can never tell us exactly where on the road, you know, which people need to boil the water and which can't. And I think their uncertainty stems from the fact that there's a lot of tanks all over the place that are actually pressurizing the network. It's not pressurized just from pumps that are left on all the time. And so I think the nearest reservoir that actually is pressurizing the water in your house may be one of the options. But then the water company also, they do have pump stations, and it's possible that they could have an enclosed, it would be pressurized, you know, like where they have a place for the water to go. I can think of out where I live in Ona, there's a pretty big building by the side of the road that has a couple of pumps in it, and it makes me wonder if there's another one of these surge tanks in there as well. But how do you actually know for sure how far the length is? I think maybe the best way would be to try and close a valve really quickly with a stopwatch and see.
But so the shockwave actually goes all the way to the reservoir.
It goes to some place where the water level can expand.
Oh, okay.
Yeah. So like where's the nearest place that that shock wave can be relieved, I guess is the short answer. It's either one of those shock absorbing pipe fittings that we saw, the guy with the washing machine, or it's just looking for a free surface. And it doesn't even have to be open to the atmosphere either. That surge tank could be enclosed and it would still serve the same function. If it was enclosed, then that's going to, here's our pipe, and here's the surge tank, and the water's continuing. If the surge tank is partly air and partly water, then that air is going to compress, but it still is going to be a lot easier for that air to compress than the water to compress. If we looked at the compressibility of both, air is millions of times more compressible than water is. All right. So for the homework that you've got due, you want to look at that one?
Yeah.
That's from a couple of years ago. It certainly couldn't have anything to do with what you're going to see. Right. All you got to do is just hack into my account, figure out my password, and it's all yours. Keys to the kingdom. No, it's not that for sure. Okay, so here's problem 43. That's the one that you're doing, right? So you start with some initial guesses. I got mine to converge pretty nicely after 3 iterations, and that's why I'm so surprised. 5, you say? You were saying 15 earlier. You had a bad initial guess? Well, if you want to write down these corrected cues, I don't mind you knowing this in advance. You still have to set everything up and solve it. But at least it gives you an idea of what you're aiming for, for it to be converged.
Use a phone to take it. Just mine are off. Like hundreds or thousands.
So mine says 0.089. What does yours say?
Like 0.0876.
0.0876. And so if we rounded off, that would be 0.088, right? Pretty close. Let's see what this is saying, because it's not exactly 0.089. It's yeah. Well, I bet it's fine. All right. So there you have it. If you want to use that as a reference. Question? Oh, really? Oh, galvanized iron. That may be it. Thanks for fixing my solution. So what KS value do we use for that one? EF? That could be the source of the difference. So let me copy that down to the rest of the iterations. Oh, I'm definitely slacking, guys. I never said I'm perfect. All right, here we go. Is that closer to your solution then, right? Okay, great. So, good luck on the homework. Everybody get the pictures they needed? I mean, it's on the video, so. All right.
My brain's not working 100%.
All right.